Greetings. We are Team 24058, AIAA Design Build Fly. Our goal was to design, build, and fly an urban air mobility vehicle that could complete emergency medical transport, air taxi, and aircraft delivery missions. We attempted a rather unique tandem wing design, and clearly it did not end quite how we hoped, but we will talk more about that later. Our aircraft needed to be able to take off in a short distance, carry a heavy payload, and fit into a parking space 2.5 feet wide. We decided that a tandem wing design would give our aircraft these characteristics. We needed wings that would provide us high lift at low angles of attack to aid us with achieving the shortest possible takeoff roll. From an airfoil comparison, we concluded that NACA 4415 was our ideal choice. Unswept wings with a 7.5-inch chord were chosen for simplicity, with each wing only protruding 12 inches from either side of the fuselage. Through research, we found that early tandem wing aircraft often suffered from control problems when the rear wing was on the same plane as the front wing, but these issues were fixed when the rear wing was placed higher than the front wing. We implemented this on our aircraft to avoid such an issue. We chose a simple controls configuration where the front wings have ailerons, the rear wings have elevators, the vertical stabilizer has its rudder, and the engines provide some differential thrust. When we researched options for receivers to utilize in the aircraft, we found our best choice was an AR637T DSMX 6-channel receiver from Spectrum. The servos we chose for all control surfaces are the HS82 MG micro analog Metal Gear servos. Design guidelines specified that the aircraft needed a door for the cockpit or a hinged cockpit canopy, and the fuselage needed a separate door to allow the payloads to be placed into the cabin. We found it easiest to implement a hinged canopy onto the cockpit, and the design of the fuselage door was straightforward. The cockpit itself was initially short and blunt to minimize mass, but some concerns about drag led to a redesign for improved aerodynamics. Plastic shrink wrap was chosen for the skin of the aircraft because of its availability, lightweight, and ease of application. Design guidelines specify that the aircraft should be able to withstand a load factor of 2.5, but research led us to conclude a maximum load factor of up to 4 was more realistic based on the aircraft's intended missions. A semi-monocoque fuselage was chosen to minimize weight, and the wings use a typical rib spar structure. Material-wise, we ultimately determined that a combination of 3D printed parts, balsa wood, and carbon fiber was ideal. Mounts for the engines were designed to allow enough ground clearance for the large propellers. Speaking of the engines, our aircraft utilizes two Avian 5065 450 kV Outrunner brushless motors supported by three-bladed 11-inch diameter propellers, a combination chosen for its high thrust. The motors were set up to counter-rotate to eliminate potential yaw effects from motor torque, and static tests of the motors showed they produced a combined thrust of almost 15 pounds. The rest of the electrical system consists of two Avian 80-amp brushless smart ESCs and two 22.2 volt 4000 milliamp hour 6S30C LiPo batteries from Spectrum.
Our prototype is mainly 3D printed using nylon, PLA, and PETG. We also used carbon fiber tubes for the wings and rods for the fuselage. Once all of the parts were printed, we test fitted and assembled our prototype to ensure that all parts were printed correctly and fit properly. From there, we began by epoxying the wings together and the fuselage, starting with attaching the airfoils and the motor mounts to the carbon fiber tubes for the wings and the carbon fiber rods to the fuselage skeleton, along with the wing mounts and landing gear in the fuselage. After epoxying the wings, we used a monocoat wrap to wrap the wings, first using an iron to apply the wrap and get it in place, and after we successfully wrapped the wings, we used a heat gun to better smoothen out the monocoat and allow for a sleeker, low-drag finish. Once the wings were fully wrapped, we took the 3D printed control surfaces and attached them to the wings using aluminum rods, and attached push rods to the control horns that were attached to the control surfaces to allow the servo motors to move the control surfaces. Then, once the fuselage was fully epoxied, we wrapped the fuselage with the same monocoat, following the same technique as we did for the wings, then attaching the wings to the fuselage with epoxy. After the entire structure and wrapping of the prototype was successfully finished, We ran wiring through the wings for the motors and the servos into the fuselage to connect to the ESC and receivers to all of our electronics on the aircraft. With the prototype constructed, we had begun ground testing the differential thrust and the various control surfaces. Almost everything worked correctly, except a couple of the control surfaces were reversed. During the process of reprogramming the controller to fix the errors, an unfortunate setback occurred that caused the left motor to go to full throttle, and in doing so, the plane began to roll forward and the propeller collided with wooden blocks that were intended to hold the aircraft in place. This caused the propeller to shatter, shred the side of the cockpit, the leading edge of the wing, and rip the motor and motor mount off of the wing. The extensive damage seen in these images we determined that we could reassemble and repair our prototype. So we began first by reassembling the motor mount and reattaching the motor to the wing using epoxy. Once the structure was repaired, we rewrapped the leading edge of the wing, the motor mount, and the side of the cockpit. We then tested the structural integrity of the repaired wing and determined that it would be fit for flight. We then went out to an airfield to conduct our flight tests for the prototype. As seen in this first clip, the prototype hit a bump on the runway, causing the aircraft to bounce and rip the landing gear off of the plane and come skidding to a halt. After this first test, we analyzed the damage and saw that the failure had occurred where the landing gear attached to the fuselage, and determined that the 3D printed part for this attachment was not sufficiently strong enough for the torque that was applied due to the tall height of the landing gear. We then discussed and determined that the plane was still capable to attempt a second flight test using a throw-launch method to test the airworthiness of the aircraft. Unfortunately, this test was not successful. The damage caused in this test was extensive to the front wing and vertical tail. Preliminary analysis suggests a couple of different factors. They could have been the turbulent wake from the propellers impacting lift capability of the rear wing. It also could have been the location for the center of gravity, since with tandem wing aircraft, CG is very important. The investigation into this crash is still ongoing at the making of this video on April 13th. Our final results on why the plane crashed have yet to be determined. In the end, we learned from our mistakes and from the engineering design process, and we plan on passing on our knowledge to future students who participate in this project to help them succeed.